didn't happen. I can tell you about a good one though, in case you want to play one on your friends. Anybody have a good April Fool's joke has ever been played on them? Let me tell you about a good one real quick before we get started. So my husband tends to have a few interns with him every semester. And one year he told the interns that there's somebody that wanted to, we work with youth here in Conway. And he said, hey, there's some people that have some concert tickets for this band coming to town. And I need you to call this guy. His assistant will probably answer, but I want you to call and tell him that we want to get the tickets for our youth group. And he said the guy's name is Bear, B-E-H-R, like Bear Paint, if you've ever been familiar with that brand of paint. And Bear, Mr. Bear. So he gave him the number to the Little Rock Zoo. And so they called and asked to talk to Mr. Bear. And the lady at the Little Rock Zoo was like, I'm sorry, I don't think, and they called again. He did this to 3 people, guys. That's my husband for you. You can't ever trust a word he says. So anyways, if you want to play a prank on somebody, do with that what you will. Have them call the Little Rock Zoo and ask to talk to Mr. Bear. It was so funny. We were remembering it last night. Okay. Gases. Much more riveting stuff. Here's where we left off. We talked about the properties you use to, hold on, sorry, in the chat, I feel like this is good. In 9th grade, a kid pretended to break a Chromebook in front of our teacher and had the broken screen picture on there, and she had a heart attack. Oh, that's good. Did you say 9th grade? Man, that's smart. You 9th graders. If I think of any other ones, I'll try to share. But all right. Okay, gases. Pressure, volume, temperature. So we introed these ideas, and we talked how pressure is force per unit area. And then, sorry, I'll keep sending stuff in the chat. I'm convinced a teacher, I saw a rat in her room and she spent 10 minutes looking for it. That's so good. We talked about PSI, okay, pounds per square inch is a unit of pressure. And then we talked about atmospheres, okay, and 1 atmosphere equals 14.7 PSI. Another unit of pressure was the millimeters of mercury, and the nickname for that is the torr, but torrs aren't going to be on the exam. And then there's one more unit of pressure that I wanted to introduce to you guys. So that is on this next slide. Finally, it says we have the SI unit of pressure, okay? SI unit of pressure. So remember, there's a whole kind of brand of units that are international units. And this is important so that people who publish articles and in medicine and research can communicate globally. So for pressure, the unit is the Pascal, PA. And pascals are the smallest, very, very small. 1 ATM equals a ton of pascals. It's 101,325. And we're actually going to work a problem a little bit later with kilopascals, which should be no big thing. You know what kilo means, right? So what that means is that 1,000 pascals equals 1 kilopascal, okay? I don't know if kilopascals will be exactly on the exam, but for later in today's lecture, I wanted to mention kilopascals. But here's really the big thing. I want you to know that 1 ATM is equal to 760 millimeters of mercury, 101,325 pascals, and 14.7 PSI. These are all, you can convert in between these freely, right? So we're actually going to do a problem really quick. And I know there's a homework problem where it asks you, it gives you like, 30 PSI, how many ATM is this? 30 PSI, how many millimeters mercury is this? So on and so forth. So we're going to work a problem just like that actually now. And this is going to be a big deal because when we get to gas laws, there will be times where you have 2 different pressures given to you. Okay, it may say the gas initially starts out and the pressure is 2 ATM. And then when things change, parameters change. Oh, somebody said, can you go back up? There, Kai, is that good? When things change, maybe have something in millimeters mercury, okay? If you're given 2 different units of pressure for a gas law problem, you have to make sure you convert to the same unit, okay? So that's why what we're doing gas law. Let me make sure I'm getting some feedback on something. All right, I think that's good. Okay, so here's the problem. Your tire pressure is 34 PSI, or it should be 34 PSI around that. What is this in millimeters mercury? Okay, so we need this info up here. PSI, millimeters mercury. We need these two numbers. We're just going to write a conversion factor, start with 34 PSI. We want to cancel units of PSI, pounds per square inch. We want to convert to millimeters mercury. So grab your calculator or your phone or whatever. I need help with this. 34 PSI times, we want to do 14.7 PSI on the bottom and 760 millimeters mercury on the top. So once you have it set up like this, PSI cancel. So we'll do 34 times 760 divided by 14.7. What do y'all get? $1,757.82 seems to be confirmed. Right? So again, these are simple one-step conversions. The only way they complicate problems is that sometimes you got to do this little, conversion first before you plug your numbers into your gas law. Don't forget that, okay, or get the wrong answer. All right, next, if we want to know how many pascals this is, you can start with 34 PSI again, or you can just take your answer in millimeters mercury unit and convert straight to Pascal. So we want to cancel millimeters mercury and convert to Pascal. So what are the numbers we need? Just go right back up here. This time we want to convert pascals and millimeters mercury. So we're going to do 760 millimeters mercury on bottom, 101,325 pascals on top. Okay, again, one-step conversion. Or you could have done 34 PSI to pascals. Either way, you just use the numbers for that. I'm just kind of continuing from my previous answer. So do 1,757.82 times the 101,325 and divide that by 760. Okay, Kiara got 234,357 pascals. So it's a lot of pascals. Like we said, pascals is the smallest unit. So usually your answer in pascals will be a big number, and that would make more sense. Okay, what about in atmospheres? So if we wanted to convert 234,357.14 pascals. Again, this number of pascals is equal to this many PSI. So you could start with 34 PSI or just this number of pascals. Lastly, we're converting from pascals to ATM. Whoops. So we need those numbers. So 1 ATM, this time we're doing 1 ATM and the pascal number. We want pascals to cancel. I like ATMs because usually the numbers are a lot smaller and easier to manage than numbers with pascals. Pascals cancel. How many ATM is this? It should be like a small number, like a number, actually probably even between 1 and 10. Haley got 2.31. Is that what everybody else got? Haley got a 2. Okay, good. All right, so these make sense. Again, none of this is terribly difficult, but sometimes it can be a nuisance because you got to do this before you can just plug everything into your problem, okay? But it's easy things. That's why I wanted to work a few problems on it. Just always check, and I'll remind you again when we actually work a problem with a gas law to look for this, okay? Make sure your units match and know how to convert between these units. All right, now we're actually going to get to gas laws. So I'm going to start with one of the two major laws I want you to be ready and prepared to work problems with on the exam. This is the combined gas law. And so you see units, P stands for pressure, V for volume, T for temperature. You see all these units in the equation. What's difficult about this equation is there are 6 variables. Okay, here's how the problem reads. you have one set of conditions on this side and you have another set of conditions on this side. So that's why you see pressure, volume, and temperature at one condition, P1, V1 over T1 equals, for any gas, the pressure times volume divided by temperature at a different set of conditions. So that's, they just call that P2, V2, T2, okay? So I encourage you, as you read a problem with all these different variables, go through and label, this number is P1, that number is V2. You'll see me do that in a little while. What this law helps us do is determine changes in the gas's physical properties. And obviously it relates pressure, volume, and temperature, describes the relationship there. So this law was built upon three simple laws, laws that you may have heard of in a previous science class. Okay, so Boyle's law, Charles' law, Gay-Lussac's law, all combined into that's why they call it the combined gas law. So to understand the combined gas law, we're going to break it down with these three simple laws. We're going to start with Boyle's law first. And again, any of these laws are laws you can pick for your bonus point opportunity. If you want to find how this relates to health science, we're going to work a really cool problem with Boyle's law in just a minute. Okay, Boyle's law is just, all of these simple laws are two of the three variables. So we see for Boyle's law, it is just pressure and volume in Boyle's law. So when you're just looking at two of the three variables, the one that's not present, or the one that we're not considering, is not part of the equation because it's held constant. Okay, it's held constant. So what is being held constant for Boyle's law? Essentially, we could ask the question, what does the combined gas law look like when the, obviously temperature is the one we're missing here, when the temperature is held constant? Well, if temperature is being held constant, we're just going to rip it out of the equation. Okay, you could plug a 1 in for that spot or just take it out completely. So if we literally take temperature out of the equation here, all we have is P1, pressure times volume, equals another pressure times volume, P2V2. So now I think this figure is a really good example, straight from your textbook. So you can go look at it in the chapter as well and kind of read if this is confusing. But the way it exemplified, kind of the visual picture it gives for these laws is, I like to think of a bike pump. Anybody tried to air up your bike tire before? If you don't have it set exactly right, you push down on it, it won't go. So if you have a cylinder like a bike pump and you have a lid with a handle that's movable, you can pull it up and out, okay? Or push it down. So if we have a cylinder like this and the gas inside, they've shaded it green for you, is sitting currently initially at a volume of 1 liter, okay? And then the pressure inside that cylinder is 1 atm. Okay, now the lid on this thing is movable, just like a bike pump would be. So if we decided to increase the pressure, what Boyle's law says, an increase in pressure, let's say we push the lid down and we've compressed that gas, okay? So the gas particles are moving around, hitting the walls, and that creates pressure on the cylinder, but they have a smaller space to move around in, okay? And that's why, one, the pressure is increasing because they're colliding with the walls more frequently because they have less space to move around, and the volume has decreased. If you push down on the lid, obviously you're going to shrink down the volume. So what Boyle's law says, what we've learned about the relationship between pressure and volume, is if temperature is constant, when you increase pressure, you decrease volume, and vice versa. If you increase volume, you inherently decrease pressure. Okay? Makes sense? So what we've learned here is that pressure and volume are inversely proportional. Maybe you've seen this little squiggle before. That's an annotation for just proportional. It says P is proportional to 1 over V, which is inverse proportions. Okay, if P was squiggle V, it'd be directly proportional, but P is proportional to 1 over V, which means they're inversely proportional. And then it has this little phrase right here, PV equals a constant. So if we multiply the pressure and the volume together, those numbers, we should get a constant. Well, how can we check that? Let's do that for both sides. P1 times V1 on this side is just 1 times 1, right? What about on this side? We get 2 times 0.5. Whoops, there it goes. Equals 1. So we get the same number. And that should hold true for any gas. When you're holding temperature constant, volume and temperature, when you multiply those, because they're inversely proportional, will give you the same number. Will give you a constant. Okay, now we're actually gonna work a really cool problem. You don't think it's cool yet, but I'm gonna convince you that's cool. I literally pulled this out of an article, okay, from last year. And this is an article. It says using Boyle's law, P1V1 equals P2V2. An example of a way it applies to health science, you can literally use it to calculate the change in volume at different altitudes. Okay, how would this apply to health science? Well, sometimes patients have to be med flighted, right? And usually those are scary situations. For example, a patient with a simple pneumothorax. The first time I read this, I was like, a huda, huh? A pneuma what? I had to look the term up. Maybe some of you health science people that work in hospitals or have jobs in hospitals knows what that is. What is that? Anybody know what a pneumothorax is? I bet somebody knows. Yep. Thank you, Bailey. Collapsed lung. Okay. Collapsed lung. So they're being airlifted to their local hospital. They have a collapsed lung with a volume. Right now, their lung has a volume of 1,500 milliliters at sea level. Okay, and then it says parentheses 101.3 kPa. What is that? 101.3 kPa. Do you recognize these units now? Tried to give you a heads up on these. Kilopascal. So this is a pressure. So here's what I'm gonna do. I'm gonna go in, I'm gonna label this. So right here, this is, I'm gonna have to write really small. This is V1. That's the first volume that we're given. Then I'm gonna go over here, this 101.3, this is P1. This is the first pressure that we're given. So again, annotate your problems as you read these, it'll help. Okay, that's at sea level. And then it says at an altitude of 1 kilometer. So they get in the helicopter and they go up 1 kilometer above sea level. The pressure, what do you notice? The pressure decreases to 90 kPa. So this is, let me zoom in. This is P2, the second pressure. Assuming the patient remains at constant temperature, calculate the volume of the lung, the collapsed lung. So as pressure decreases, what do we expect to happen to volume based on what we just learned about Boyle's law? If pressure decreases, volume would what? Increase. That could be dangerous. Why? That lung is already damaged a little bit or not working properly. We don't want to expand it too much. Okay. So here's what we got. P1V1 equals P2V2. Which variable are we looking for? Which one do we need to solve for? Tyler said V2. Okay, so we are trying to solve for V2 right here. So always, if you remember problems with specific heat density, this is some algebra now. You got to rearrange your equation, isolate the variable you are trying to solve for. And these things are multiplied. Okay, it's P1 times V1, P2 times V2. So what do we need to do to get V2 by itself? Yeah, Haley, divide by P2, cross divide. Cross divide meaning I do it on both sides. Okay, and then P2 goes away, it cancels on that side. So my new equation is this, V2 equals P1 times V1 divided by P2, all right? Okay, this is what you're gonna do for all these problems, even stuff like combined gas law and later even with the ideal gas law. Always rearrange your problem first, assess what you're solving for. That's okay, Carol. That's Kira. Always rearrange your problem and isolate what we're solving for. Now let's plug everything in. By the way, we've got 2 units of pressure, or sorry, 2 terms for pressure. Or do they have the same units? You have to always check for that. Do I need to convert or can I just plug it straight in because I have the same units? I think I have the same kPa on both, so I'm good. Now, if it was like millimeters of mercury in kPa, you need to convert and get them both on the same page. But we're good here. So we're just going to say this equals P1 is 101.3 kPa times 1,500 milliliters. Milliliters is fine. And not divide that by 90 kPa. So units of kPa will cancel. We'll just be left with units of milliliters. So what'd y'all get? Haley got 1688. So 16 V2 is 1,688.33 milliliters. So the volume of the lung, as we expected, expanded. Does anybody know what average lung capacity is or should be? The lung's not going to explode on us, is it? It's not too much, is it? Anyways, you could look that up. That would be my question. Is this expansion dangerous? What do we do? Do we need to fly back down, lower elevations? So anyways, that's an example. I thought it was a pretty cool problem, how you solve. This is exactly the stuff I'm looking for. Something similar. It doesn't even have to be a full problem like this. I had such creative examples from students in the fall, things they found of how gas laws relate to health science. Okay. All right, questions on this? Not too bad, huh? All right. Charles' law. Now we're assessing the relationship between temperature and volume. So what are we holding constant? What is the combined? Sorry, in the chat, hold on. If you have to convert the pressure so that they are the same unit, does it matter which unit we use? No, just so that they're both the same. Yeah. Essentially, I'm going to sneeze. No, I'm not. Okay, no, I'm not. The combined gas law. What does the combined gas law look like when we hold the pressure constant? All right. So we're just going to erase pressure, take that out. So now Charles' law is just V1 over T1 equals V2 over T2. Okay. So keeping with our little cylinder bike pump analogy, we're given the initial terms here. P1 is 1 atm. Our volume, V1, is 0.5 liters. And now we're given a temperature down here, 200 Kelvin. That's T1. T1. So what if we heat this up? We're looking at the relationship between temperature and volume. So pressure is going to be the same on both sides, okay? So if we heat it up, what did we do? We doubled the temperature. So this is T2. If we go from 200 Kelvin to 400 Kelvin, what happens to volume? Again, the lid is movable here. It can slide because we're keeping the same pressure. So if we're going to keep the same pressure, volume has got to increase. What happens when you heat things up, molecules? They move faster. Heat is a form of energy, okay? So we're adding energy to all these gas particles, okay? So it's like you put 10 people in an elevator and you heat it up. If they're gas molecules, they just start running around faster and faster and faster. And so they're going to collide with the walls of the container more often, which would typically inherently increase pressure. But because the lid's movable, it's going to increase the volume so that pressure remains constant. Okay, that's what Charles' law says. It's exactly the way a hot air balloon works. Anybody been in a hot air balloon before? This is another thing. Besides going to Iceland, I want to go on a hot air balloon ride. There's how it works. You heat up the gas, okay? You crank up the temperature. So the gas inside the balloon, those particles start moving around, and that's what inflates the balloon, okay? Now, the reason that a hot air balloon rises off the ground after it's inflated, is because the density of the air inside the balloon lowers. Okay, because the expanded volume, you have the same mass of the gas inside. We know density is a relationship between mass and volume. So the mass stays the same, but the volume grows, so the density lowers. And remember, things that are less dense, they rise. Okay, that's why things that are less dense float in water. So a hot air balloon rises because of that. It's exactly Charles' law, is exactly kind of describes how a hot air balloon works. Okay, so what we learned is that temperature and volume are they proportional or inversely proportional? If they're inversely, as one increases, the other decreases. If they're directly proportional, as one increases, the other increases too, by the same proportion. So look at these. If we double temperature, what happened? Volume doubled as well. So these are proportional. All right, so T squiggle V. T is proportional V. And V divided by T is a constant. You can always double check that. You could do 0.5 divided by 200 here. What do you get? And then do 1 divided by 400 here, and you should get the same number. Okay. Questions on Charles' law? All right, Gay-Lussac's law. Last one, we're looking at the relationship between the last two things we have not yet looked at. So temperature and pressure, Gay-Lussac's law. So if we're looking at temperature and pressure, what's being held constant? Essentially, what does the combined gas law look like when the, well, volume here is held constant? So we're just gonna take volume out, or you can plug in a 1 for volume, whatever you like to do. P1 over what's left is P1 over T1 equals P2 over T2. So this Gay-Lussac's law, what does it mean with our little picture analogy here? So volume is fixed this time. It's gonna be 1 liter on both sides. So now the lid is not movable. So now we're just gonna heat up the gas and see how that affects the pressure on the inside, okay? So if initially we have 200 Kelvin is our T1, and we heat that up to 400 Kelvin, what happens to pressure? Volume stays the same, so the lid doesn't move. So the gas particles are moving faster and faster and faster, colliding with the walls. What it does is it doubles the pressure. Just the way it doubles the volume, it doubles the pressure. Okay? So just like Charles' law, volume and temperature are directly proportional. Also, pressure and temperature are proportional, directly proportional. All right. So those are the 3 laws that combine into the combined gas law. We're going to work problems on the combined gas law in just a little bit. I want to introduce some other laws though. So we're going to kind of keep pushing through this content for a minute, and then we'll work a lot of problems at the end. So that's the combined gas law. I'll put a pin in that for just a minute. I want to introduce a new gas law that's going to set us up for the ideal gas law. Okay, so again, the combined gas law and the ideal gas law, those are the 2 you need to be ready to work problems on for the exam. Indirectly, Boyle's, Charles, Gay-Lussac's if I tell you something's held constant, but know those 2, combined and ideal. So let's look at now something a little different. It's called Avogadro's law. Okay, this is not because it has Avogadro's number in it. Okay, that's a different thing. This is Avogadro's law on gases, which is just examining the relationship between the volume of a gas and then how much gas is present, the molar amount. Okay, moles, grams indicate a quantity, a mass. So I want to ask you this question. Which balloon has more moles of gas in it? Okay, if we blow up a balloon with helium gas, which balloon has more, the blue or the red balloon? The red, obviously. So what does this tell us? As volume increases, as the volume of a gas increases, what happens to its molar amount? Does it increase or decrease? More moles of gas occupies a larger volume, okay? So the relationship between volume and molar amount is also proportional, okay? They're gonna increase or decrease together. It's pressure and volume that are inverse. That's the only relationship there between those 2 parameters are inverse, is one increases, the other decreases. The rest of these, they are proportionally, directly proportional. So the next slide is a little bit more of a definition of Avogadro's law. At constant, here's the deal. This one's a little different. We got 2 things being held constant. At constant, I'll try again. At constant pressure and temperature, the volume of a gas is directly proportional to the molar amount. And that makes sense. Just think of the balloon picture we just saw. So we're going to abbreviate volume with a V and number of moles of gas with an N. With an N. So what is Avogadro's law? How would you guys write it? Based on what you just saw with Charles' law and Gay-Lussac's law, if volume and number of moles are also directly proportional, I bet you could write this law for me. What would y'all write? Anybody have a guess? V equals N. Okay, Heaven got it. Volume over mole, well, over N, number of moles. Tyler, close. It should be V over N. Good, good, good. Allie and Maddie, thank you. V1 over N1 equals V2 over N2. That's exactly right. Make sense? Okay, in other words, in layman terms, as you increase the number of moles of gas, the volume of the gas will also increase. Is it awkward silence when I pause and let y'all think? No, it's not awkward. Have I ever shared with y'all my awkward silence story? No? It's a great time for it. I usually share this, I can't remember when I usually share this story. So, a little bit about myself. You've all wanted to know. The first time I ever went on a date with a guy. Guys, I'm sorry, this is not to hate on you. We went out to eat. I remember we got burgers or something. I just remember it's Halloween. Okay, this was my first date, and it was Halloween. So the guy's gonna be all polite. We get our food. He's like, "I'm gonna say a blessing. I'm gonna pray over our food." So I'm like, "Okay." And in the middle of his prayer, he just goes, "And God, just bless all those Halloweeners out there and keep them safe." He literally plays this out loud. I lose it. Like I'm laughing out loud while he's finishing his prayer because he'd said, "God bless the Halloweeners and keep them safe." So, guys, don't do that. Nobody do that. It's awkward. Talk about awkward. All right, back to gas laws. All right, talking about Avogadro's law, you're probably going to see this on a few problems for your homework and maybe in the back of the textbook. We're keeping pressure and temperature constant, right? So oftentimes what they'll do is they'll say at STP, there's this condition, they just kind of abbreviated it. At standard temperature and pressure is what that stands for, STP. So when you're doing rules or laws or problems that involve Avogadro's law or even the ideal gas law, it's kind of nice to have a standard set of conditions that you can run experiments at or try things at, and that way you can compare your results a lot easier. That's kind of the purpose of standard temperature and pressure. But what is standard temperature and pressure? 0 degrees Celsius or 273.15 Kelvin and then 1 atm. That is the actual condition. So in those cases, if it says STP and it's an ideal gas law problem, I'm just introducing this so you know what numbers to plug in for your temperature and your pressure. But at STP, what they've learned is 1 mole of any gas. I was kind of surprised by how big this was, 22.4 liters. That's quite a big amount, right? 22 liters. That's the standard molar volume of any gas. 1 mole of a gas occupies that many liters, that volume. Okay. So that's Avogadro's law, and that is setting us up. I wanted you to kind of get familiar with number of moles of gas so that we can now look at the ideal gas law. But this slide is just a review. This is just all the laws. Again, if you were taking my class in person and we could not use our notes and could not have things open note, which they would not be. So don't tell your friends next semester or whatever that my exams are all open note because they won't be. But I would have you just memorize the combined gas law. Okay. That's the main one you need to focus on, and then know how to manipulate that or remove a term if something's being held constant to get any of these other laws. Except for Avogadro's. Avogadro's not part of the combined gas law. It is setting us up for the ideal gas law, okay, which is this. The relationship between pressure, volume, temperature, and moles of gas. Okay, so this one kind of doesn't one up on the combined gas law because it's relating all those three terms plus number of moles of gas. So all this is combined into a single equation known as the ideal gas law, which is this. PV equals the pressure times the volume equals the number of moles of the gas times R. What is R? We'll introduce R in a second. RT. PV equals nRT. Sometimes I wish for these things. Anybody learn the quadratic formula in a song? Like did your math teacher teach you X equals, yeah, okay. I wish there was a song for this one, and you still remember it. You still remember that equation because of that song. So, sorry, in the chat, kind of off topic, but would this apply to something like shaking up a Coke or carbonated drink, make the bottle feel firmer? That's why it spews. Exactly. It also has to do with like why sodas go flat if they're like at a warmer temperature. So one time I bought a whole case. We drink, don't make fun of us, but we drink the no flavor carbonated water. It's like our favorite drink at our house. Just the plain old Kroger brand. Doesn't even have to be fancy LaCroix. So we drink that. Well, I bought a whole case one time and I left it in, I drive a minivan. I left it in the back of the minivan one time and it was summer and I forgot about it for like a day. And then I went to get it and the whole case was flat. I was so disappointed. But all of these gas laws have to do with why things like what you just mentioned, Bailey, in the chat happen, especially with carbonated drinks, because there's gas involved, right? They really aren't that, but thank you, Keegan. I know, right? You should try them. Don't hate on them. They're good. Okay. R is, by the way, we need to introduce R. It is a constant whose value in units do not change. No, what? You don't like carbonated drinks? You like sodas, don't you? You just take out the sugar. It's a constant whose value does not change. So when P isn't, by the way, you can look up gas law constants on the internet. You might find a few different ones. Okay, so don't do that. Just stick with this one. This is the one you're going to use, right? R equals 0.0821. That's the number for R. It does not change. You're going to plug this in every single time for the ideal gas law. And may I introduce the variable with the single largest number of units yet that we have seen, okay? You thought delta S was a lot of units, calories per mole Kelvin. This one has 4 units in it, liters times ATM on the top, mole Kelvin. And yes, you have to write all 4 every time. So R is going to be important. And when you work an ideal gas law problem, it is very, very important that all your units, look up here on these other terms, volume, pressure, number of moles, and temperature, that all the units here must match the units in R, okay? So if you're reading a problem and it says the pressure is 60 psi and it's an ideal gas law problem, guess what? You've got to convert that to ATM before you can plug it in, okay? Everything has to match units on R. Here's an actual problem for ideal gas laws. How many moles of air are in the lungs of an average person with a total lung capacity of 3.8 liters? 3.8 liters. Assume that the person is at 1 ATM pressure and has a normal body temperature of 37 degrees Celsius. Okay, Tyler, I'm surprised you haven't said, but what about above average people? You usually have a good remark for problems. 3.8 liters, 1 ATM, 37 degrees Celsius, okay? So we're going to plug this in to PV equals nRT. So what are we solving for? Some of you don't even know where to start right now. What is your question asking for? How many moles of air? Okay, so we're going to solve for N. N, that's the variable for number of moles. So the first thing we need to do is rearrange our equation to solve for N. So PV equals nRT. And we want to solve for N. So what do we need to do? We need to cross divide both sides by actually 2 variables here. We got to move R and T. So we're going to cross divide both sides by RT. And those will cancel on this side. And then our new equation we'll write out is that N equals pressure times volume divided by R times T. Gas constant times temperature. Now we need to check, do all of our units on everything match R? So let's go in and see. Lung capacity is 3.8 liters. That matches R. We got liters in R. So that's good. We don't have to convert there. 1 ATM, that's for pressure. That matches R, so that's good. Temperature, 37 degrees Celsius, does not match R. So we got to convert to Kelvin. So that's the only really, always double check these. Sometimes you might have to convert 1 or 2 things before you can plug in. 37 degrees Celsius plus 273.15 equals what? 310. Now we can plug everything in. So N equals P is 1 ATM times V, which is 3.8 liters. And it doesn't matter if you write V first or P first, okay? Just as long as you're multiplying pressure and volume. Divided by RT. So now we're going to plug in R. And I will say I've already had one student email me from the morning lecture. It's 0.0821. Don't forget the 0.0. I know there's lots of numbers here. 0.0821. And it's L times ATM over mole, right? All the units. And then this is R, and you do R times the temperature, which we solved for, 310. So look what happens with the units. ATM on top right there, and in R, you've got ATM. Those cancel. Liter on top, liters from the R term cancel. Kelvin is in the bottom of the units for R, and right there, those cancel. Everything cancels except for moles. You got 1 over moles, which is just units of moles. So I encourage you, put this top part in parentheses in your calculator, this bottom part, if you're going to do it all at once. 1 times 3.8 divided by, in parentheses, 0.0821 times 310.15. What do you guys get? How many moles of gas is this in our lungs? 0.15 moles of oxygen. Okay, Lucy, 0.1492. 4 decimals. I like that. Very good. Whoops. Okay. I'm sorry. That was funny. You can laugh. That was awkward, and I don't know what to do now. Whoa. I actually don't even know who that came from. I can only see like 20 at a time, so be thankful. Usually the screen lights up green if you're talking, so I don't know. That was my best friend in the back. Well, she got some crazy stuff going on. Okay, entertaining. And you thought chemistry class was boring. Okay. Woo, I don't even know how to move on from that. Okay, here's what we're not going to talk about because we're kind of done with the content, but we are going to work problems. Do not leave. If you leave, you are going to miss out some good stuff. But I feel like we've covered so much content now. We need to take a breather and work a few more problems. Okay, we need to actually work a full combined gas law problem. Tiara, your roommate's going to get you now for unmuting and let us all hear that. I passed them. Here they are. Okay. Gas has a volume of 300 milliliters at 300 millimeters mercury. So here's the deal. Here's what's going to happen on the exam. You're going to read a problem and you're going to be like, how do I even know what equation to use? I got so many equations in my portfolio of equations. Which one do I use? So I'm going to teach you how to dissect it and figure out, okay, which equation do I use? Well, first off, if it says a gas or some kind of gas or helium gas or whatever, it's probably a gas law problem. Has a volume of 300 milliliters at 300 millimeters mercury. I keep saying millimeters. This one's milliliters. This one's millimeters mercury. Okay, what will the volume be if the pressure is changed to 500 millimeter mercury? Okay, so looking at the units, let's go through and label what kind of properties these are, like volume, pressure, temperature. Let's just see what we have. So I notice 300 milliliters. That is units of volume, okay? So V1, 300 millimeter mercury. That's a unit of pressure. So P1. And then 500 millimeter mercury. That's another pressure. So we're going to label that P2. All right. So what is this looking like it should be? It says, what will the volume be? So we're looking for another volume term. So we got P1, V1, P2, and V2. So what kind of law does this look like it could be? Boyle's law. I'm sorry, I can't stop thinking about shaving off breath. I'm sorry, I can't move on. All right, P1, V1 equals P2, V2. Okay, so again, if you just go through and annotate your problem, that's going to help you discern what law you should use. So now we're just going to, she's so embarrassed. Well, fortunately for her, we don't know her, okay? So we won't even know if we see her in Walmart. All right. So you're just going to plug everything. So we need to rearrange the equation for V2, by the way. So first you need to cross divide by P2. And it's going to cancel out on this side. So now you just plug everything in. And what's nice, you also have to double check. Do I need to convert anything pressure-wise? I got two different pressures. And no, you don't. It's just millimeters mercury, right? On both. Now, if it was like millimeters mercury and ATM, then either way, you just convert them. Doesn't matter which one you convert to, just so that they're both the same. Okay, so we're going to do 300 millimeters mercury times okay, so this is plugging everything in. We're solving for V2. Yeah, I'm having a really hard time focusing. Just gonna admit that. We'll do the best we can. How much time do we have? We still have like 20 minutes. Wow. Okay, equals V2. See, this is the kind of stuff when we're back in person. I'm gonna miss this. These moments are hilarious. That only happen on Zoom. You're gonna go tell. I bet some of you. How many of you have already texted your friends? Oh my gosh! Listen to what just happened in my chemistry class. No.
All of my roommates heard what was going on. They're all sitting here.
Wow, this is gonna go viral, guys. I'm crying literal tears right now. Oh my gosh. I can't. It's like when you're in church and you're not supposed to laugh, and so that just makes it funny, and you just keep laughing. That's how I feel right now. Oh my gosh. Okay, anybody get V2 yet, by the way? No. Oh my gosh. Haley just reminded us, it's recorded. I can't. Although it's gonna be in the middle of lecture. I can't stop laughing. Oh, I'm a crier when I laugh really hard. It's seriously it's gonna be on the recording. Y'all are all I'm gonna get the most views on YouTube I've ever gotten because y'all are all gonna go watch this recording now. Oh. Okay. What's the freaking answer for V2? It's 180 milliliters. Wow. Oh. All right, I'm done. I'm done laughing. 180 milliliters. Anybody have questions on this problem? I feel like I did not even explain it. You plug everything in, make sure units of millimeters of mercury cancel 180 milliliters. Okay. Next one. I really do want to get through these problems so that I help you guys for the exam. A gas has a volume of 350 milliliters at 45 degrees Celsius. I can't. I'm not done. I thought I was done. I'm not done. If the volume changes to 400 milliliters, what is the new temperature? Report the new temperature in degrees Celsius. This actually, I do want to talk about an important thing. You have to work gas law problems in units of Kelvin, okay? Units of Kelvin. So you are given a temperature in Celsius, and it's asking for the answer in Celsius. So what's seems very convenient, would be very simple, is for you to just work it all in Celsius. But you will get the wrong answer, okay? Because you're two different temperature scales. I know they're proportional temperature scales, but you have to make a note, work things in Kelvin. Always convert to Kelvin. So let's go ahead and do that. 45 degrees Celsius plus 273. I think it's 318.15 Kelvin. Okay. By the way, we got to figure out what gas law we need. So we got, if you annotate your problem, if you go in, kind of like I like to do, you've got a volume here. So I'm just going to say V1, and you got a temperature. So I'm just going to call that T as the first temperature. Got another volume, that's V2. Yep, Charles' law. Okay, so this is a relationship between volume and temperature, and then what's the new temperature? So we're solving for T2. So if you take out pressure, obviously we're not dealing with pressure. We're not even given a pressure unit. And it doesn't necessarily tell you pressure is held constant. But if you see that you have nothing to do with pressure here, just take pressure out. So it's V1 over T1 equals V2 over T2. So we need to solve for T2. So how are we going to rearrange this? There's two ways you can go about this. One is a long way. The other is a shortcut. And I'm all about some shortcuts. So look, T2 is in the denominator. Here's what some of you would do. Some of you would say, oh, I'm going to cross divide by V2, and then I have T2 by itself. You would say V1 over V2 T1, and that gives me not T2. That gives you 1 over T2. Some of you would do that, though. Don't do that on the exam. That's wrong. So let's erase and try again. So it's V1 over T1 equals V2 over T2. Here's what you do. Here's a shortcut. Flip the whole equation. I promise this is legal to do. Okay, flip the whole equation and get T2 in the top. So it's literally becomes T1 over V1 equals T2 over V2. Now move V2. What you need to solve for always needs to be in a numerator, not in a denominator. So now you cross multiply both sides by V2. Cancel. Okay, now T2 is by itself and it's in the top. So now you can plug everything in. You're going to get your answer in Kelvin, convert back to Celsius. So let's see if I can shrink this down a little bit. This is why I love iPads. Anybody with me? Some of you use iPads. I see you bring it into lab. V2. So let's go find V2. I'm going to highlight it. It's right here, 400 milliliters. Times T1. Okay, so where's T1? 45, but we converted that to Kelvin. So times 318.15 Kelvin and divided by V1, which is the 350 milliliters. By the way, you can always check yourself like a concept check. You know that if temperature increases, volume increases. If temperature decreases, volume decreases. So look, volume is starting at 350 and it's increasing to 400. So what should happen? Well, your answer in temperature wise should be bigger, right? If volume increases, temperature increases. So your answer should be above 318.15 because volume and temperature are proportional. So if you get an answer that's below 318, you probably did it wrong. What do y'all get? 400 times 318.15 divided by 350. Okay, Autumn said 363.6. Okay, so that is T2. So then you would just convert that back to Celsius by subtracting. You would do 363.6 Kelvin minus 273.15. What do you get? Kennedy got 90.45 degrees Celsius. All right. That's that one. This is another really good one, hairspray. If you heat it up, the pressure eventually becomes so much that it'll explode. I'm going to skip over this one right now because I actually want to spend a moment working an entire combined gas law problem. So far, what we've worked is just like the Boyles and the Charles. I want to work a whole gas law problem. I'm just going to say this. I was having a rough morning and that just made my day. Good. I'm like on the brink of busting out laughing every 5 minutes. Trying to hold it together over here. Okay. Oh my gosh. It seriously is going to be on the recording. I would take it out, but I'm not that skilled in my editing. I can trim the beginning and the end, and that's it. Whoa, okay. 862. This is back before, if you can tell, I haven't edited these slides in a bit. This is back before I had access to the electronic text. So I literally take the textbook and put it on the scanner and scan it, and you have this beautiful copy of the problem that you see here. So we're gonna work this one. I don't know if you can read it. It says a gas has a volume of 2.84 liters at 1 atm and 0 degrees Celsius. What temperature does it have when you have a new volume of 7.5 liters, 520 millimeters mercury? Stop. I'm going to turn all your videos off because y'all keep laughing. I can't look at y'all. By the way, now if you didn't have this header here, you'd probably read this. And again, some of you would be like, how do I know what law to use? Okay, the header here is telling you you're going to use the combined gas law. So it's all the variables, all 6 pieces. P1, V1 over T1 equals P2, V2 over T2. But if you're just reading this on the exam, here's what I want you to do. I want you to annotate it. So I'm just going to go through. We're just going to label everything. It's a volume. The first thing we see right here is a volume. So I'm just going to say V1. The next thing I read, it says at 1 atm. This is the pressure. So I'm just going to call that P1. And 0 degrees Celsius, there's T1. Then the question begins. At what temperature? So this, what we're looking for is T2. Does it have a volume? At what temperature does it have a volume of? So it gives us another. Well, I meant to erase. There's V2, units of liters, and P2. Okay. So once we got everything labeled, you got P1, V1, T1, P2, V2, and you're looking for T2. We've got 5 of the 6 pieces. This is for sure combined gas law problem. Okay. Now you need to make sure, before I just plug everything to the equation, what do I need to check for? Yep, that the units are the same. Do you see any that we need to convert? Pressure, thank you, Bailey. Right here, we have ATM, but down here for P2, we have millimeters mercury. And thank you, Lucy. Lucy reminded us we need to convert that to Kelvin. Okay, so we got 3, just 2. You can do it one of 2 ways. You can pick P1, which is the ATMs, and convert it to millimeters mercury, or vice versa. I'm going to put everything in ATMs because I just like to work with those numbers better. They tend to be smaller and sometimes whole numbers. So what I'm going to do is I'm going to take P2 and I'm going to convert to units of ATM. All right, so we got 520 millimeters mercury. And we need to convert this to ATM. So I'm going to zoom in really quick. I'll be back. 760, that's the magic number, of millimeters of mercury equals 1 atm. And if you're like, where did I just get this relationship? Scroll back up to when we were talking about units of pressure. You got all those relationships listed for you. So you're going to cancel millimeters mercury. How many ATMs is this? This just keeps getting better. My friend, she said she wants everyone to know. She was tongue crammed someone by not stating a fact. Thank you. We'll believe her. All right, so this equals 0.684 ATM. Oh my gosh. Tyler said he got 7.2. Anybody get something different? Anybody agree with Tyler? Is it because I use a phone calculator? No, it's probably because you're just Tyler. I'm just kidding. Anybody else got? I got, okay. Okay, seems like 6.8 is the answer. That's what we're gonna go with. Okay, now we're also gonna convert T1 to Kelvin. So 0 degrees Celsius, this is easy, right? That equals 273.15 Kelvin. Okay, now we're ready to go. good, Tyler. You can admit your mistakes. Okay, so we need to solve for T2. So what is the equation? P1 V1 over T1 equals P2 V2 over T2. Uh-oh. Uh-oh, what we're solving for is in the bottom. So before you go plug in all the numbers in and all the units, yes, Bradley, exactly. You just flip the whole dang thing, okay? T1 over P1 V1 equals T2 over P2 V2. I guarantee you I'm going to get comments on my evals. Instructor could not hold it together in an intense moment in class. Some of y'all are going to say that. I know it. You're right. I couldn't. I'm sorry. Okay, so now we need to move everything except for T2. So times P2 V2. Thank you, Keegan. Times P2 V2. All right, so it cancels on this side. I'm trying to be professional here. So this is, whoops, what am I writing? P1, V1. Okay, if some of you are like, where the heck are we? I'm writing so many letters and numbers. I feel like I'm writing a different language. This stuff is new, so give yourself some grace. You got a whole homework on this stuff. We're going to do a whole review on this Monday. I'm going to assign recommended textbook problems. But yes, it's a lot of units and numbers and variables. So this all equals T2. The biggest thing is you make sure you're not solving for 1 over T2. Now we should be able to plug everything in from here on. So where's P2? This one, this is the one we had to convert. So we got 0.684 ATM times V2, 7.5 liters times T1, which we converted to Kelvin, 273.15 Kelvin. We're going to divide that by P1 and V1, okay? P1 is 1 ATM and V1 is 2.84 liters, right? So what do you guys get? 0.684 times 7.5 times 273.15 Kelvin. If you notice, you probably did, ATMs cancel, liters cancel. This is what should happen. You should end up with just the unit you need for temperature. We're solving for T2. So what is T2? 493.4 Kelvin. All right. Okay. So that is a combined gas law problem. We worked a combined gas law problem. We worked ideal gas law problem. Did a lot today. We would have finished like 10 minutes ago, but you know, we had some fun entertainment. So we know we are using the ideal gas law when it has moles in the problem. Yes, Keegan, that's one of the main things I want to point out today. How do you know which law to use? Okay, there's a lot of different laws here. When your problem has moles, so I'm going to scroll back up to that ideal gas law problem because Keegan is exactly right. So see this problem, it says how many moles? Or if you're reading a problem, it says you've got 5 moles of a gas and here's your pressure and here's your temperature, blah, blah. If it has moles in it, that is ideal gas law. Why? Because the combined gas law has no variable for moles, okay? Would we change that to degrees Celsius? Yeah, Madison, we forgot to do that, didn't we? So we got the answer for T2 and it said, wait, did it? No, it just says what temperature. If it asks specifically for Celsius, then convert it. But here, Kelvin is fine. Okay, if it does not specify, Kelvin is fine. All right. That is the conclusion of another eventful day in chemistry 1402. Do you guys have any questions? I'm gonna stop sharing. If I need to go back, I love this class. Aw, I do too. Well, stop it. When will the video be posted? I like this much more than chapter 7. Matt, it'll be posted soon enough. I'm gonna download it I got lab this afternoon though, okay? So I can't do it this afternoon. Probably after that. Please do. My friend says this. You'll at least get an A in the class now. I bet she will get an A in the class because she's a great student, is why. She took it like a champ. She just owned it. Okay. Going to Keegan says, do we have to print anything off the lab? Yes, please print off the PDF. That will make it